This is a block stacking robot. Upgraded RC servos with a custom smart servo driver and the combination of stereo camera measurements allow it to freely manipulate and stack blocks on the stage. In this video, I'd like to take you along on the journey of developing this robot. The impetus for this project was my desire to make the SG90 servo move smoothly. I've poured a lot of passion into creating compact robots. In that pursuit, the SG90, a small and inexpensive RC servo, was a very powerful ally. But a problem arose. Take a look at the movement of this robot. This is a companion robot I made earlier. I wanted it to express emotions by moving its arms and such, but its movements are very jerky. I'm using SG90S in the joints, but I wish they would move more smoothly. So, in this project, I decided to develop a custom smart servo driver that allows PID gain settings and current angle acquisition via I2C communication. To verify its performance, I thought of creating a Servo robot and, together with a camera, aiming to achieve the goal of stacking blocks. Let me briefly touch on how the SG90 works. The SG90 can rotate to a specified target angle. Therefore, if you specify target angles that change slightly at very short intervals, you should be able to pseudo-control the rotation speed. But when you actually try this, it moves jerkily like this. Why does it move this way? RC servos like the SG90 are controlled by PWM signals. PWM signals send pulses by varying the voltage in this shape, and the servo is controlled by the proportion of time it is on within one wave. In the driver of an RC servo, the capacitor charges only during the on time of the PWM. Therefore, the longer the on time, the higher the voltage the capacitor holds. Then, this voltage is compared with the voltage determined by the angle of the potentiometer. By passing a current, which is a constant multiple of the difference between these two voltages, to the motor, it changes the angle so that the voltage difference becomes smaller. This is called proportional control. However, with proportional control, when the target angle is very close to the current angle, the current flowing to the motor becomes too small, and the motor actually stops rotating. Therefore, for example, even if you give the SG90 a target angle that increases by 1 degree every 20 milliseconds, the motor won't move until the difference between the current angle and the target angle reaches about 10 degrees, and then it suddenly starts moving. This is the reason why, when you try to control the speed of the SG90, it moves jerkily. But you might think, if we increase the proportional gain in this equation, it should be able to respond to small angle differences. However, in reality, if you set a large proportional gain, it vibrates like this. To suppress this vibration, derivative control is necessary. Derivative control outputs in a direction that suppresses angle changes, so it can reduce vibrations. With derivative control, you can set a large proportional gain, respond to small changes in the target angle, and still suppress vibrations. However, the SG90 probably doesn't have this derivative control. Therefore, to suppress vibrations, the proportional gain has to be made small, and as a result, it cannot respond to small target angle changes, leading to jerky movements like this. So, I designed this smart servo driver. Utilizing a small microcontroller like the STM32, it can control the angle of the SG90 using PID control as an I2C slave. Additionally, from devices like a Raspberry Pi, you can set PID gains and torque and read the current angle, angular velocity, and output. Therefore, you can adjust it to the optimal settings according to the robot it is mounted on. Let's actually use this driver to move the SG90. As you can see, we can control the angle smoothly without vibrations. Now, leaving further technical details for another video, let's look at the block stacking robot to test the performance of this servo driver. An action that is very simple for us, stacking blocks. How can we have a robot replicate this? Let's break down this goal into several tasks. First, we need to find the blocks. We humans can somehow sense where the blocks are, but that's not the case for robots. An algorithm is needed to accurately obtain the three-dimensional coordinates of the blocks. Next, we need to pick up the blocks. Our human hands are probably the most excellent in the natural world, so picking up blocks is a piece of cake. But it's challenging for robots. Someone once said, if robots attack, just close the door. Because it's very difficult for robots to turn doorknobs. Well, recently, robots can open doors too, but anyway, we need an end effector that can pick up blocks. And of course, we need to accurately move the end effector to the position of the found block. That be why combining these three tasks, stacking blocks, can be realized. First, let's implement the task of accurately moving the end effector. I designed an arm robot like this. For the structure of the arm robot, I adopted the most basic Servo robot this time. A Servo robot has two links with a mechanism that moves up and down at the end. It's simple to control and excels at horizontal movement, making it perfect for bringing blocks over other blocks. The rotation angle of the SG90 is plus or minus 90 degrees, which is a bit insufficient for the joints of an arm robot. So, I use timing belts and gears to expand the rotation angle to plus or minus 138 degrees. I repositioned the built-in potentiometers of the SG90 here and here. For the up-down mechanism, I adopt a ball screw, enabling smooth lifting of blocks. This is the original servo driver. It supports USB PD, allowing power supply up to 5V5A. With this servo driver, I can control 3 SG90s, 2 for the links and 1 for the pump used with the vacuum pad. And this other driver here is for controlling the ball screw, supporting angle acquisition with a rotary encoder. By the way, this design has a fatal flaw. Can you figure out what it is? I spent a lot of time dealing with that mistake after assembling the robot. I'll touch on it later, so please try to find it. Now, how about the robot's design? While incorporating the golden ratio appropriately, I aim to give it a cute yet sophisticated impression by giving it a rounded form. When I was designing, I saw a shiny yellow bicycle in the neighborhood and thought it was a nice color, so I made the main color of the robot yellow. By using transparent parts, we can see the movement of gears and timing belts from the outside. It tickles the hearts of those of us who love machines. Now that the robot design is finished, let's actually print it with a 3D printer. But what should we do about these particular transparent parts? Those who have tried it will know, but commercially available resins are not actually very transparent. And when you do secondary curing, they become yellowish and cloudy. This is a prototype of another robot I made before with transparent resin. Also, printing all these parts in this quantity is really tough. That's where this project sponsor, JLC3DP, comes in. JLC3DP, the future of manufacturing with advanced 3D printing services. Their streamlined online platform allows for easy upload of 3D models, instant quotes, and real-time order tracking. From material selection to the speedy delivery of final products, they meticulously manage every step, with production times as fast as 24 hours and delivery within just 2 days. By watching this video and becoming a new JLC3DP user, you can receive up to $60 in coupons. Check out what JLC3DP can do for you at the link below. Alright, the parts have arrived from JLC3DP, so let's go ahead and check them out. First of all, I want to say that creating the print data for this many parts, actually printing them, cleaning the parts, removing the supports, and polishing them requires an enormous amount of time and patience. With JLC3DP, all you need to do is upload your model. But of course, the most important thing is the quality. Take a look at this. First, even the larger parts that are prone to warping have been printed beautifully without any distortion. Next, the smaller parts like gears that require precision have also turned out perfectly. The transparent parts are also very clear, without any yellowing or cloudiness, and look excellent. Furthermore, the metal parts are just right for areas where strength is essential. I highly recommend JLC3DP. Now let's start assembling the robot. There's not much to say during the assembly process, so I thought I'd fill the time with some witty commentary. But then I realized that since I usually either make robots or watch YouTube, I don't have much to talk about at times like this. So, I'd like to take this opportunity to talk about my next project. What I want to tackle next is creating a quadruped robot like Boston Dynamics Spot or Unitree's Go series. I plan to build brushless motors, ESCs, and reducers from scratch to achieve dynamic movement. I'd also like to challenge myself with more advanced features, like using cameras for self-positioning and environmental mapping. There are many technical challenges ahead, but that just makes the project all the more rewarding. Actually, the reason I started making robots was because of a humanoid robot called Roby. Its adorable appearance and lovable design captured my heart. I love creating product designs and cute robots that people can embrace, and I've poured my efforts into such projects up until now. This year, as a fourth-year university student, I've also started working in a research lab. I feel the need to tackle more advanced technical content, and in that context, I see the quadruped robot as a challenging yet achievable goal, despite its technical difficulties. In fact, the smart servo driver I developed for this project was originally intended for the quadruped robot. A quadruped robot requires 12 actuators, and I was experimenting to see if I could enhance inexpensive high-torque RC servos with my custom smart servo drivers. However, I realized that RC servos lack sufficient torque, making it difficult to create a quadruped robot with smooth movements. Even so, through this project, my anxiety about PCB design has significantly decreased. I now have the confidence to create the ESCs for brushless motors needed in the next project. I plan to start by making brushless motors, cycloidal reducers, ESCs, and so on, and I'd like to showcase the process in videos. However, building the entire quadruped robot is likely to require quite a bit of material cost. Therefore, I'm planning to launch a crowdfunding campaign soon. I would be truly grateful for your support. Also, I've started a membership on this YouTube channel. If you'd like, please consider joining. In the membership, I'll be sharing the latest project updates in short videos every 2 weeks. By the way, what kind of robots are you interested in? Please let me know in the comments what features or designs you look for in a robot, or what technologies you'd like to see explored. I'd be happy to consider your ideas for the next robot project after the quadruped robot. Alright, it looks like the robot is almost finished, so let's get back to it. I was able to assemble it quite neatly. However, it was only now that I realized a fatal design mistake. It's this. I am transmitting rotation to the potentiometers using gears. Gears have gaps called backlash to allow for smooth rotation. Therefore, when the direction of rotation changes, the gear at the receiving end slightly lags in response. And this lag accumulates the more gears there are. In this robot, there are 5 gear contacts before the rotation is transmitted to the potentiometers that monitor the rotation. As a result, when the arm's rotation changes direction, the potentiometer does not rotate for a while, causing a problem. This makes precise control impossible. I completely forgot about backlash during the design phase. By the way, with this setup, it moves like this. When the joint passes the target value and starts to reverse direction, the potentiometer's readings aren't updated, so you can see the joint moving back significantly. To improve this, I reduced the number of gears and reprinted them with very small backlash. As you can see, the transmission to the potentiometers has improved. When I move it like this, it works. This should be manageable. Additionally, although I'm still using a pair of gears for this transmission, I replaced them with gears with small backlash. Now that we've somehow completed the preparations, let's move on to control. How can we freely control this robot? The Scara robot itself is equipped with 3 servos, so it has 3 degrees of freedom. Specifically, we can freely control the position of this vacuum pad in 3-dimensional space. However, we cannot control its orientation. An object in 3-dimensional space has 6 degrees of freedom. It has 3 values for how much it translates in the X, Y, and Z directions, and 3 values for how many degrees it rotates around the X, Y, and Z axis, which fully determine the object's orientation. Therefore, if an arm robot wants to completely control the position and orientation of the object it is holding, at least 6 actuators are necessary. However, our goal this time is to stack blocks, so what we need are the movements in the Z-axis direction to lift the blocks, and the movements in the X and Y-axis directions to bring the lifted blocks over other blocks. Therefore, 3 motors are sufficient. First, let's think about inverse kinematics. Such an arm robot is called a 2-link model, and is the first model introduced in textbooks. Therefore, the way to solve it is very simple. However, solving equations is boring, so I'll just show the results here. By substituting the desired coordinates X and Y of the arm's tip into this equation, you can find the required motor rotation angles θ1 and θ2. With this, you can now move the arm's tip to your desired location. However, look closely. The trajectory of the arm's tip is not a neat straight line. Right now, the robot is only instructed to move the arm's tip from this starting point to the end point. How it moves in between is not controlled at all. The method to solve this problem is very simple. You just need to specify the coordinates of the trajectory when moving between these points. This equation is the linear equation of a straight line moving from the starting point to the end point. By increasing the parameter s from 0 to 1, it goes from the starting point to the end point. Let's incorporate the concept of time into this equation. Suppose we want to move the arm's tip over t seconds. Let the current time be t, and replace s with t/t. By changing t from 0 to t, the specified coordinates move from the starting point to the end point. Now, with this equation, we can also control the trajectory of the arm's tip. Look at this. It's moving more straight than before, isn't it? See with your mind's eye. Look, it's straight. However, there is still room for improvement. If we focus only on the x direction in this equation and plot it on a graph, it looks like this. The velocity graph is like this. Furthermore, the acceleration graph is like this. We can see that the acceleration becomes theoretically infinite at the start and end of the arm's movement. Of course, in reality, the robot is accelerating finitely, but even so, large acceleration occurs. According to Newton's equation of motion, the product of acceleration and mass is force. So if large acceleration occurs, a strong force is applied to the robot's parts, which can cause failures. Therefore, the trapezoidal velocity profile was conceived. As the name suggests, it's a method of designing the parameter s so that the shape of the velocity graph of the arm's movement becomes a trapezoid. With this, the acceleration graph looks like this. You can see that the acceleration is finite. When we actually move the arm based on this trapezoidal velocity profile, it looks like this. Compared to before, you can see that the speed is slower at the start and end of the movement. See with your mind's eye. By the way, is it best to move the arm in a straight line? The workspace of the Servo robot has this shape. The workspace is the range within which the arm can move. For example, when moving the arm linearly from here to here, the arm goes out of the workspace during the movement, making it impossible to realize. Therefore, by using polar coordinates, let's move the arm first by rotating in the theta direction. Then, if we move linearly in the r direction, we can move the arm without going out of the workspace. With this, the first task of being able to freely move the end effector has been achieved. Congratulations! Next, let's implement the task of picking up blocks. This time, I adopted a vacuum pad as the end effector to pick up the blocks. This end effector has two functions. First, it obviously vacuums, and it moves up and down to control the z-coordinate. First, let's look at the function of moving up and down. The movement generated by the motor is rotational, so we need some kind of mechanism to convert that into linear movement. This time, I adopted a ball screw. Its mechanism is similar to a screw and nut. Screws and nuts have helical grooves, and by rotating them relative to each other, they move linearly. The ball screw has balls in the groove part. These balls roll, reducing friction and allowing the rotational movement to be converted into linear movement without wasting energy. The ball screw designed this time has a pitch of 4 millimeters. In other words, when the ball screw rotates once, the end effector moves down 4 millimeters. Also, a rotary encoder is attached to the ball screw to monitor rotation. This rotary encoder clicks 24 times per rotation. So by monitoring the number of clicks with the STM32 on this servo driver, we can know that if it clicks 24 times, it has moved down 4 millimeters. Expressed in an equation, it looks like this. Here, n is the number of clicks required to achieve height z. Next, about the vacuum pad. I designed a pump like this to generate suction power. I can suck in air with the SG92R. With this, we can suction the blocks and lift them. Finally, let's implement the task of finding blocks. This time, we use two cameras to perform stereo measurement and identify the three-dimensional coordinates of the blocks. How can we know the three-dimensional coordinates based on this principle? First, let's consider this problem when there is only one camera. Suppose there is an object at x, y, z in a coordinate system with the camera lens's center as the origin. Suppose that object is projected onto you V on the image with a focal length f. Can we determine the three-dimensional coordinates of the object from U, V, and F? The answer is no. We cannot measure a single point in three-dimensional space. However, we can determine the straight line on which the object exists. However, we don't know where on this straight line the object is, so we use another camera. Let's look at the object from another angle. Then, as before, we can determine the equation of the straight line connecting the lens center of the second camera and the object. The object exists on both of these straight lines, which means that the object's coordinates are at the intersection of the two straight lines. This is the most basic concept of stereo measurement. However, in actual cameras, due to manufacturing errors, distorted images are projected onto the sensor. Therefore, camera calibration is necessary. By photographing a checkerboard from various angles, we examine the precise characteristics of the camera's lens, focal length, image sensor, and so on. These are called the camera's internal parameters. This allows objects to be accurately projected onto the image. Now, if we know the position and orientation of the cameras, we can perform stereo measurement. But how do we determine these? We need to consider the PNP, perspective and point problem. The PNP problem involves estimating the most plausible position and orientation of the camera when at least 4 known 3D coordinates are projected onto an image. In this case, we'll use these 24 points on the stage as known coordinates. We can freely decide these points during the design phase. By ensuring all the points are within the camera's field of view, we manually click on them to obtain their coordinates in the image. With this, we have all the conditions necessary to solve the PNP problem and can estimate the camera's position and orientation. These are called the camera's external parameters. Now, if we paint the blocks red, we can obtain images like this. Since the largest red contour in the image is the block, by finding its centroid, we can know where the center of the block is projected in both images. Therefore, using that information along with the camera's internal and external parameters, we can determine the block's three-dimensional coordinates. Now, all the tasks have been achieved. We can now move the robot arm to the target position, lift blocks with the vacuum pad, and determine the coordinates of the blocks through stereo measurement. So let's immediately try moving the arm to the block. A problem has occurred. The vacuum pad does not go over the block. Why is that? This is due to discrepancies between the model used in calculations and the actual robot. In this case, using potentiometers to acquire angle measurements means that errors during joint calibration significantly impact precision. Additionally, the actual robot may bend under its own weight. However, since we have cameras this time, let's apply feedback by obtaining the coordinates of the end effector through stereo measurement to move it precisely into position. After moving the arm to the approximate position, we correct it until the error is within 3 millimeters. We've now successfully managed to move it directly above the block. Now let's try again. After calibrating the joints, we obtain the coordinates of the 4 blocks. Since there are 2 blocks of each color, we need to correctly match the 2 sets of line equations. The lines from camera 0 to each red block are projected on a camera 1's image like this. At this time, each line passes through the corresponding block, so we use this to perform matching. This is called epipolar geometry, an important concept in stereo measurement. With this, we can determine the coordinates even if multiple blocks of the same color appear. Since we've obtained the coordinates of the 4 blocks, we arrange them to be stacked in the order of blue, red, blue, red. Now let's actually try stacking the blocks. The arm moves to the first block by combining circular and linear movements. It failed to grab it. It seems there's an air leak. I fixed it. Let's try again. It's a failure. It's a failure. It's a failure. Despite making numerous adjustments and repeated attempts, I was ultimately unable to stack all 4 blocks. The main factors believed to have caused the failure are the low air tightness of the vacuum pad and the low precision of the robot. Because positioning the arm took time, air leaked from the vacuum pad during that period, resulting in the block falling. Including the time spent studying, I worked on this project for 4 months, so it's regrettable that I couldn't achieve the block stacking. However, I was able to acquire new skills that will be central in future projects, such as designing servo drivers and understanding the basics of stereo measurement. These skills will undoubtedly be valuable in my next project. Thank you for watching until the end. All the CAD files, PCB manufacturing data, programs, and more from this project can be downloaded from the link in the description. Please take a look if you're interested. If you like, please hit the like button and subscribe to the channel. See you in the next video.